continue with the ambiguous grammar. This particular example, the grammar is the statement derives if expression then statement, or if expression then statement else statement, or other. Let us have this string. If capital E1, then if capital E2, then statement 1, else statement 2. So let us consider a parse tree for the string. Look at this. First, the start symbol. So what is the start symbol here? stmt. I'm going to replace this stmt with the first rule, that is if expression then statement. And after that, the statement can be the last one. The statement can be replaced with if, the second rule, if expression then statement else statement. Now substitute for expression E1, expression E2, statement S1, statement S2. So this is one parse tree. Is it possible to construct another parse tree for the same string? Let us try. Why we have to select the first rule for the statement? Let us select the second rule. Okay. So what is that second rule? If expression then statement else statement. So now for the statement, let us select the first rule. If expression then statement. Now expression is replaced with E1, E2, S1, S2. So if expression then if E2 then S1 else S2. So here also look at the first one, if expression then if E2 then S1 else S2. Same, right? Okay, for the given string we have two parse tree. But the thing is, here we can eliminate the ambiguity. So let us change the grammar now, so slightly. So how to change the grammar? Let us consider, so this is the grammar, the variant of the first one. That means we can rewrite the dangling else grammar as the following unambiguous grammar. The idea is that a statement appearing between, listen carefully, the statement appearing between a then and else must be matched. That is, the interior statement must not end with an unmatched or open then. A matched statement is either an if then else statement containing no open statement, or it may be any other kind of unconditional statement. Hence we have this grammar. Okay, that is statement derives matched statement or open statement. Open statement means it starts with then. Okay, open then. Matched statement. What is matched statement here? If expression then matched statement else matched statement, that's it, or other. But what is open statement? If expression then statement and if expression then matched statement else open statement. Okay, so for same example you try to construct a parse tree. Okay, so you will get only one parse tree. Just try that. Okay, elimination of left recursion. Top-down parsing method cannot handle left recursive grammar. Therefore, the transformation is needed to eliminate left recursion, okay, from the grammar. So how to say the grammar contain left recursive property? Let us consider this definition. A grammar is left recursive if it has a non-terminal a such that a derivation a derives a alpha by application of one or more time. Plus stands for one or more time. By application of this, so we have on the right hand side a alpha for some string alpha. Look at this particular grammar. So a derives a alpha. Left hand side also we have symbol a, right hand side also we have symbol, the first symbol is a. So this grammar is left recursive. So how to eliminate left recursion from the grammar? If the rule is like A derives A alpha bar beta, so this grammar has property, right? Left recursive property. So how to eliminate that? So let us introduce one more symbol that is called as A dash. That is A derives beta. So that is the second production, beta A dash. Then what is A dash? A dash derives alpha A dash bar epsilon. Without changing the string derived from A. Means the first grammar, whatever the rule that is before the first grammar. So that is nothing but A derives A alpha bar beta, right? And after that we replaced with the another grammar. Both grammar are same. This rule by itself suffix for many grammar without changing the string derivable from A. So this is the general form. So A derives A alpha 1, A alpha 2, etc. A alpha n bar beta 1, beta 2, beta n. So how to replace this? So A derives beta 1 A dash, beta 2 A dash, etc. beta n A dash. What is A dash? Alpha 1 A dash, alpha 2 A dash, etc. alpha n A dash bar epsilon. So we have one algorithm, so that is used to eliminate left recursion. Let us study later, okay, how this algorithm works or helps to eliminate the left recursive property from the grammar. Now let us consider, so let us have one example. So you will understand this concept, how to eliminate left recursion from the given grammar. So what is the grammar here? The grammar is E derives E plus T bar T, T derives T star F bar F, and F derives bracketized expression bar ID. Okay, so this is the example. Now look at the first production here. What is that? E derives E plus T bar T. Whether this has left recursive property? Yes, because according to the definition, this is of the form A derives A alpha bar beta. What is A here? It is nothing but E. What is alpha? Alpha is nothing but plus T. What is beta? It is just anti. Look at the color. Okay, so brown color and the blue color and the red color. Okay, so what is alpha? Remember, alpha is plus T. What is beta? Beta is T. So how to remove the, let us apply, okay. So apply the formula as it is. So how to remove the left recursive property? That is by replacing A derives beta A dash. Okay, what is beta here? T, right? Therefore, E derives T E dash. Understood? Okay. Now what is the next step? What is A dash? We introduced one more non-terminal, right? So A dash derives alpha A dash. What is alpha here? Plus T. Therefore, E dash derives plus T E dash bar epsilon. Clear? So now consider the second production, that is T derives T star F bar F. Again, this is left recursive. Hence, we have to remove this. How to remove? Okay, so what is A here? T. What is alpha? Star F. What is beta? It is just F. So let us replace that. T derives F T dash. Then what is T dash? T dash is, what is alpha here? Star F, right? Star F T dash bar epsilon. So in general, the grammar is E derives T dash, E derives plus E T dash bar epsilon, T derives FT dash, T dash derives star FT dash bar epsilon, and the last one doesn't have the left recursive property, hence no change. So F derives bracketized expression bar ID. So this is the modified grammar. Okay. Now one more example. So what is that? S derives SA small b capital A derives capital A capital A bar capital B, and capital B derives A small a. Okay. So let us consider the first one. What is that? S derives capital SA bar B capital A. Okay. So this is of the form A derives A alpha bar beta. What is A here? Capital A. That is nothing but capital S. So left hand side and right hand side having same symbol. What is alpha? It is small letter A. Okay. What is beta here? Beta is equal to small b A. So what is the change now? What is the replacement actually? The replacement is A derives beta A dash. So what is A? S. S derives B A. B A means it is beta, right? B A S dash. So we introduced one more new symbol S dash. What is S dash? S dash is A. A is alpha. A S dash derives epsilon. Okay. So let us consider the second production. That is A derives A small a capital A bar B. Again this is left recursive property. So what is the changes here? Alpha is A capital A, beta is just B. Therefore, the first replacement is A dash derives B A dash. And what is A dash? A dash is A capital A, that is alpha, right? A capital A dash derives epsilon. Hence, the modified grammar is okay this one, because the last what is that B derives A doesn't have left recursive property, so we'll write as it is. Now let us consider one more example. The grammar is S derives capital A small a bar B. Let us denote as a production 1. A derives capital A small c bar SD bar epsilon. Look at the production 1. Okay, S derives capital A bar B. But this doesn't contain any left recursive property, right? S in the left hand side and right hand side we don't have S at all, the starting symbol. Hence, don't conclude it doesn't have left recursive property. Look at the production A. So A derives AC and the second one is A derives SD, right? In the place of A, if I substitute SD, now what happens? Now this grammar suffering from left recursive property. Okay, fine. So now let us consider the second production. A derives A small c bar SD bar epsilon. So in the place of yes, I apply grammar 1. That is, in the place of yes, you just substitute. So we'll get AC bar AAD bar BD bar epsilon. Hence, this is the modified grammar. So this is the input for now left recursive algorithm. Okay, now let us change. So the first grammar doesn't have any left recursive property, but according to the second one, left hand side also A, right hand side also A. So let us make the changes after applying the left recursive property. So this will be the modified grammar. So we know the general formula, right? So A derives A alpha 1 bar A alpha 2 etc. beta 1 bar beta 2 etc. beta n. After apply the left recursive property, so we'll get this answer. I think you have so many confusion. How you got modified grammar, right? See, we have an algorithm. Let us have that algorithm. Let us consider we have the production 1 and the production 2. And let us have this algorithm. Okay, let us eliminate the left recursion using this algorithm. What is the input here? The grammar G with no cycles or epsilon production. But here we have something called the epsilon production, right? So don't worry, the epsilon production is harmless here. Actually, this algorithm doesn't work because of epsilon production, but this epsilon production is harmless. So let us apply the algorithm now. Okay, input is grammar G. And what is the output? Equivalent grammar, no changes, but with no left recursion. Try to understand. Okay, so we'll get the equivalent grammar with no left recursion. Now let us apply the algorithm to this particular production, grammar production. See what we have to do. So here, look at the algorithm step 1 to step 7. The step 1 says that arrange the non-terminal in some order, that is A1, A2, etc. AN. Okay, so what is the non-terminal in our grammar? It is nothing but capital S and capital A. How many non-terminal? Exactly 2 non-terminals. Okay, therefore we can say non-terminals are only 2, that is small n is equal to 2 and they are S comma A. Understood? Now let us consider the step 2 to 6, 2 to 7. If we apply this in the previous slide, we got something like the modified grammar, right? So this steps 2 to 7, okay? So after applying this 2 to 7, we'll get the modified grammar. So now let us consider the step 2. I is equal to 1 to n. So what is the value for I now? How many non-terminals? Exactly 2. So I takes only two value, that is 1 and 2. Look at that. I is equal to 1 represent the first rule and I is equal to 2 represent the second rule. Okay. Now for the inner loop, what is that inner loop? For j is equal to 1 to I minus 1. Now first time you consider I is equal to 1. Okay, I is equal to 1 means the rule is the first one. S derives A bar B. Now let us compute what is J. See, J is equal to 1 to I minus 1. What is the value of I? I is equal to 1. 1 minus 1 is 0. So inner loop first time fails, right? For the first production, inner loop fails. Hence, the body of inner for loop doesn't execute. Now what we have to do, we have to select I is equal to 2, which is the production. A derives capital AC bar SD bar epsilon. Okay. Now let us execute again the inner loop J. So what is the value for J now? J is equal to 1 to I minus 1. That is 1 to 2 minus 1. That is 1 to 1. First time. The condition only once executes, right? Only one. So what we have to do, condition is true, therefore we have to replace a production of the form AI derives AJ gamma. Okay, what is AJ? AJ is equal to delta 1 bar delta 2 etc. delta k. So we have to replace that. In the place of AJ, we have AI derives delta 1 bar gamma, sorry, delta 1 gamma, delta 2 gamma, etc. delta k gamma. See, look at this. In the production, A derives AC bar SD bar epsilon. Okay, you have to identify what is AJ. What is AJ here? It is nothing but yes. Okay, we have for yes, what is the production? AA bar B. Okay, rule 1. So after applying that, so what we'll get? It is nothing but the replacement. AC bar AAD bar BD bar epsilon. See, try to understand. We are not replacing for rule 1 because according to this algorithm, the rule 1 condition fails. But for the rule 2, the condition is true, right? Therefore, we are applying the substitution, okay, for SD. Clear? Okay. So next, what is the value of I? Okay, only there are two, right? I is equal to 1 and I is equal to 2. When I is equal to 3, condition fails. So algorithm closes. Therefore, we got the modified grammar. So that is S derives AA bar B and A derives AC bar AAD bar BD bar epsilon. Now, let us consider for the first rule, whether we have left recursive property for the first rule. No, only we have left recursive property for the rule 2. So apply that property. So we'll get